will have seen this, lecture 2, which is on the early universe, and perhaps you'll have questions about what I'm presenting here. And as you will soon see, I have also some supplemental information that results from questions and conversations I've had since last week's meeting. So let's get started. First thing I want to show you is, I think I had mentioned this, the Hubble Deep Field. This is a series of photographs produced using the Hubble Space Telescope. This one is a particular interest, and it's called, as you see in the title, it's called the Hubble Extra Deep Field. The Hubble Deep Fields Hubble Deep Fields are these very inspired photographs done over long periods of time. In fact, you'll see once again in the title of the image, 2 million seconds of exposure time that took 10 years to assemble, just by pointing the telescope repeatedly at the same spot on the sky. And the telescope is so good in terms of pointing control that you can take a picture and then you can look away, take pictures of other objects, and then come back and precisely point at the same thing again. It's really extraordinary technology. And we have this little panel over here showing the relative size of the moon and the size of the patch of sky for which this photograph was taken. And the importance of these deep fields is the telescope is pointed at an area that appears to be totally dark. That is, in between the stars and the galaxies that have already been photographed. Here we have this spot that's just seems to be devoid of information. But if you stare at this spot for 2 million seconds, look what appears. These are the oldest galaxies that we've ever seen. And remember in the first lecture I showed you categorization of galaxies developed by Hubble. Many of these galaxies are really, they're not in that categorization because they're very primitive. These date back to the time when galaxies first formed, and many of the galaxies we see now are not represented in this picture. But there's hundreds and hundreds, perhaps thousands of galaxies in this patch of sky. So that's the Hubble Extra Deep Field. And there's tons of information on this on the internet if you want to get more details. Okay, this is a page I think almost all of you already have, pointing to where various of my lectures are, and my YouTube channel, and a set of lectures I did on a ship in December. Won't spend a lot of time. Some of you have asked about recommended reading. So I've just put these little patches together, things I think are good. Here's me with Neil deGrasse Tyson. His series called Cosmos is generally available. I don't know if it's available on YouTube, but most of you have something like Apple TV or Netflix or something, and you might be able to find that there. It's very good. And it's the new version with Tyson. The original version, which is also very good with Carl Sagan, is something you might want to look at. Brian Greene has some pretty advanced books. No equations, but the concepts that he addresses are out there. This is a wonderful book by Hawking, wonderful illustrations. One of my favorite guys, John Wheeler, who just died a few years ago at the age of 96, a real expert on gravitational science. He has this book. This is a fun little book, got a lot of cartoons. It's written for people of every age. I was starting to say a 12-year-old could read this. No, a 9-year-old could read this. It's got little cartoons and amusing things. This is Kip Thorne's wonderful book on black holes. Scientific American as a resource can't be beat. It's a science magazine that comes every month and it frequently addresses the topics we're interested in. Two books about Einstein. This one by uh, Abraham Pais is particularly good because Pais worked with Einstein up until Einstein's death in 1955 or so. And the Isaacson book became a series on TV. You might be able to find that. Dramatization of Einstein's life. Interstellar, a technically accurate, this is not a science fiction film. Almost everything in this film is either known to be possible or nobody knows of a reason why it's not possible. And there's a companion book. For those of you with some advanced math background, you really want to get serious, click on this link. Ed Taylor has a book that he gives away for free, a very excellent book on Einstein's theory of gravity, done in a way that somebody, for example, an engineer, you don't have to be a gravitational scientist to use that book. An engineer, somebody who teaches math, something like that, you might find that book good. Here's a selection of pictures I took during the cruise in December in the ocean. These three pictures are mine. And this one is famous. This was taken not far from where I was. I was out in the ocean on the way to India. This picture was taken in Oman where the eclipse occurred at sunrise. So this red area is the rising sun distorted by the refraction of the atmosphere. You see that bending there? And this arc is formed by the disk of the moon. So we saw the eclipse at 8:30 in the morning or so. So the sun was not near the horizon, but that's the maximum coverage that we got, something like that. Okay, from last week, before we get started on the early universe, let's talk about what we did last week. We found that there's observed structure in the universe. The distribution of galaxies has a particular distribution of areas where they're dense with galaxies and other areas that are devoid. We will explain that in a few weeks. We talked about expansion of the universe. There's still controversy related to the rate of expansion, but that's an important topic which will come up over and over during our visits. Expansion is accelerating. This is new news as of about 20 years ago, led to a Nobel Prize. And the energizing factor in the accelerating expansion is named dark energy, but we don't know what it is. We know the probable outcomes. You remember I showed you curves developed by Friedman and Lemaitre of possible futures for the universe. I already said this, dark energy is a mystery, and there's a nice link here if you want to click on that gets you to a discussion of how we know the temperature at the time the universe became transparent. We also talked about some of the challenges of visualizing the structure of the universe. And so I captured this little quote from Brian Greene's book, Fabric of the Cosmos. Remember, I said that when astronomers and astrophysicists get together and start talking about the shape of the universe, they quickly stop talking and they start doing math. And so this is a paragraph that Brian Greene wrote on this very subject. He said, you can use this spherical, like a balloon, ants on a balloon, as an analogy. That's what the professionals do. When they get together, they start doing math. So anyway, and this is a good book if you want to find out more details about multiple universes and so forth. Also, before we start, I want to talk to you about the size of the universe. I've had some questions since last time, and I want to clarify some things. The observable universe, that's a term frequently used by cosmologists. It is all the matter that can be observed here now, because light was emitted by objects sometime in the past, and there's been enough time for that light to propagate across the universe and find its way to the telescopes that we build. That's the observable universe. The universe is dramatically bigger, as I will illustrate in a second. So the observable universe has a certain size. The universe, just one word, is quite a bit bigger. But we won't see almost any of that additional space. So I've already commented on that. There is a technical term called co-moving distance. And a co-moving distance means if we could take a picture of the entire universe all at once, which of course we cannot do, but if we could take that picture, the most distant objects that produce light in the early universe are 45.5 billion light years away from us. The process of taking that picture, of course, would take billions of years because the light doesn't go at infinite speed. So parts of the universe, the vast majority of the universe, is already invisible to us and will remain so forever. It started out, these are the parts of the universe that started out near the speed of light during the expansion of the early expansion. So they started with a head start, and then with the energy of the expansion plus dark energy propelling it to even higher speeds, a whole bunch of the universe has disappeared over the horizon that contributes to our observable universe. In the future, the part of the universe that's beyond our current horizon will likely not ever become visible. There's a little technical detail which is covered in this block of text, that the Hubble expansion rate is gradually getting smaller. So there may be some galaxies that are just outside the observable universe, and that we cannot currently see or expect to see. But if the expansion rate of the universe continues to get bigger and the Hubble parameter, the Hubble constant, gets smaller, some of those currently invisible objects will enter our observable universe. And billions of years later, future astronomers would be able to see those objects. Now, there are problems with observing the most distant objects. These are the ones that are going away from us right near the speed of light. And because they're doing that, the light they emit gets stretched. And any of the light they produce gets shifted toward the red colors. And if they started out red, they get shifted to even more in the direction of red as opposed to blue. And if they get shifted enough, we just will never see them. They become undetectable. These most distant galaxies just wink out of existence. They are at the edge of the currently observable universe. Right now, the distance to the objects, the oldest objects we can see, is now about 16 billion light years because they emitted light that is just getting to us. And while it was traveling to us, they continued to move away. So we talked quite a bit about how old the universe is, 13.5 billion years. That's how long ago these objects emitted light, but they continue to move away from us, and they're currently, once again, if we could take a magical picture of the entire universe all at once, those most distant objects are roughly 16 billion light years away. There is another kind of odd possibility here. What I've described, hang on a second, I got to move some things. There's this odd possibility that the universe is actually dramatically smaller than what I've described. This is kind of an outlier theory, but it's worth talking about. It's possible the universe that we observe is smaller than these numbers that I've been throwing around, but because a smaller universe might have light in it that has propagated around the entire universe and come back more than once to encounter our telescopes, the universe could be dramatically smaller. We might be looking at objects, multiple versions of objects, and each one would look different because galaxies and clusters of galaxies evolve over time. In the early universe, there's probably a group of galaxies near where we are now that looked very different than those galaxies look now. The chemical composition changes, the number of stars, the shape. So how would we tell if we're looking at multiple generations of light propagating through the universe? This is an area of research. It would be kind of akin, by the way, to taking a picture of your child at age 3 and then and forgetting you had that picture, and then knowing your child as an adult and finding the picture and saying, are these really the same person? So this last item is kind of speculative. People are thinking about it, trying to figure out ways to determine if this is a possibility, and I thought you ought to know about that. Well, I've said a lot of this. These paragraphs are available for you to look at if you want to take the time. And once again, if you're watching this lecture between now and our next meeting and you have questions about this, bring those up and we'll have a chance to talk about it. So finally, we're going to talk about the early universe. And what we're saying is we're going to start with the Big Bang and go out 400 million years. And you'll see why that's a convenient place to stop. The first 380,000 years we'll talk about in quite a bit of detail. And we're going to talk about formation of the constituents of the early universe and how and why we are studying those constituents today. And I already said 380,000 is an important milestone in the evolution of the universe. And these are the topics we'll address. Big Bang nucleosynthesis, I abbreviate that in the lecture notes as BBN. The cosmic microwave background, that's abbreviated as CMB. And insight that Einstein's theory of gravity provides. So here's a picture of the evolution of the universe. Because I borrow this artwork from professionals. Some of them, ancient time is on the left. This one happens to have the earliest time in the universe here at the top. And here's the 380,000 years I keep talking about. That's when the universe became transparent. Prior to that, everything was so bright and energetic that it was just a cloud of pieces of the pieces of atoms. At this point, the universe was transparent but dark. There were no stars, there were no galaxies. And this area in here, going to 400 million years, this is the interval during which stars started to form, gravity drawing gas together, eventually kicking off nuclear fusion in a cloud of hydrogen gas, and suddenly we have light sources. And some of those light sources met others, some of those stars met other stars and gathered together under the influence of gravity, and we eventually get galaxies. And so this area started out totally dark, and by the end, things are getting brighter, and then we enter something we'll talk about in future weeks, reionization. But right here, this is our limit for today, from the beginning to this 400 million spot. And we're going to talk about what was going on in there. Here's the same drawing I showed you last week. It's the same kind of thing, except the dark age is in this little slice. It's just a different view of this. So this is what we'll talk about. Here's how we do in terms of different kinds of observation methods in terms of looking back in time. So ground-based telescopes in the 90s were able to look back. So these numbers are the time after the Big Bang. So ground-based telescopes of the late 20th century could look back to 6 billion years. Hubble was launched in 1990, and it looks back to 1.5 billion years after the bang. The deep field photo I showed at the beginning of this video looks way back here. It's not efficient for the Hubble telescope to look way back because, as I said, it takes thousands and thousands of hours of staring at one spot. And there's lots of things that astronomers want to look at. There's a major competition for time with the Hubble telescope. And so there are not a lot of opportunities to look this far back, but it can be done. And notice where this is. This is right after the universe, that 480 million years, or 400 million years after the universe started. By then, another 80 million years had gone by, and stars had started forming. But these images, the Hubble Extra Deep Field, is looking into the dark age when there was not much light in the universe. And here is the future hero, the James Webb Space Telescope, which will be launched next year, fingers crossed. And it's different. It uses infrared technology rather than visible technology. So it doesn't do the same thing as Hubble, but it will look way back, way into the dark age. So let's stop now. So this lecture is going to be in parts. So I'm going to stop here and make sure the video is going well. And then we'll go on to this. What does early mean?